American Fuzzer and address sanitizer. Let's give Hanno a hand.
Hello. Yeah, so I want to present a couple of tools to you today that I find extremely valuable in finding bugs and reducing the number of bugs in our software. And I feel that not enough people know about these tools, so yeah, I'm trying to change that. First, a quick introduction about myself. So yeah, I'm Hanno. I work as a freelance journalist and as I say hacker because I don't like to say security researcher or security expert because that always sounds a bit stupid. So I say I'm a hacker. I write for the German online magazine Golem and also occasionally for other publications. And I write a monthly newsletter about TLS. And I'm currently also trying to fix some things in TLS, but I'll talk about that tomorrow. And I also run the Fuzzing Project, which is an initiative founded by the Linux Foundation's Core Infrastructure Initiative. So yeah, I get paid by them for doing this. So here I want to show you an example for a relatively straightforward bug. Can anyone already see what the bug here is? Okay, so what's happening here is actually there's a memory allocation for a list of pointers or an array of pointers, and it wants to allocate space for argc number of pointers plus 2 more pointers plus a 0 terminator. And then it multiplies that with the size of the pointer. But in order to do this correctly, you need brackets around the addition. Because what you're doing here is using 3 times the size of the pointer plus argc and not argc times the size of the pointer. Everyone got that? So, and what it ends up being is that your allocated space is too small, and it's a pretty classic buffer overflow. And this is a real bug. It was in GNOME session, and yeah, the interesting thing is this bug happens every time you start GNOME. So one might wonder why it hasn't been found before. And I reported a couple of other bugs to GNOME components recently, 2 out-of-bounds reads in glib and 1 out-of-bounds reads in Pango. And all of those were triggered by their test suite. So just running make check would trigger these bugs. And to be fair, I also have to mention KDE. I found a use after free bug in QMake, which is like the build tool for Qt. And I found several out-of-bounds reads actually in Qt itself and in Kwin. The reason there's a very strange behavior of the X API, and I'm not entirely sure whether I should propose to change the X API or propose to fix those bugs. But anyway, so there were similar bugs in KDE. And the bottom line here is all of these bugs can be basically trivially found with a tool called Address Sanitizer. So by finding these bugs, I know for sure that both KDE and GNOME never tried to test their software with Address Sanitizer, because as I said, these bugs happen just by starting it. So if they have ever tested it with it, they must have run into them. So I'm sure they don't do that. Address Sanitizer is a feature which is part of your standard compiler if you're using a Linux system. So both GCC and CLang contain it integrated, and you just enable it by adding a compiler flag. So, and that's like how easy you can find these bugs. For example, the glib bug. You just like configure, I mean, you know this configure make install. When this you make configure, you add this fsanitize address, you add a G because that adds more debugging information, and then you get more useful error messages. The same thing for C++ flags, and same for the linker flags because it needs to link some library. And then you build the thing, and then you run the test suite, and then you may get these address sanitizer error messages and can learn something about bugs. So, I mean, I hope we can all agree that running these 3 commands is not overly difficult. Technically what Address Sanitizer is doing is it keeps a shadow memory which kind of records which parts of the memory you're using are currently valid memory to use or not. So if you're doing a memory allocation, it records, okay, from here to there, that's valid memory. If you call a function, the stack, that's valid memory. But it puts all these poison bytes in between. So if it does its stack allocation, unlike in a normal C program, the stack is just one blob, but with Address Sanitizer, it puts bytes between the variables. So if you read out of the bounds of a variable, it can detect that. And most notably, it finds all kinds of out-of-bounds access, both read and write, and it finds use after free bugs. And especially the out-of-bounds read and the use after free, very often they don't crash, and it's often very hard to debug when you have such a problem, because it may just be that most of the time nothing bad happens, and in some rare corner cases something crashes or something behaves in a weird way. So you get an idea what these bugs actually mean. This is a classic out-of-bounds read access. So what we have here is a actually that's not the latest version of my slide. Sorry, I have to fix that. Whatever, it's not that important. Yeah. So what we're doing here, we have an array with 2 elements, and then we're trying to access element 2, and the counting starts with 0, therefore 2 is invalid, only 0 and 1 are valid. And yeah, I have this code here. There's a small change that I put the array index in a variable that silences a warning, but so if we normally compile this, then it will just print out some garbage, because we've tried to access a value on the stack, but outside the bounds of where we wanted to, where we have our array. And now if we add this fsanitized address and debugging again, then we get a very nice error message. And it's extremely detailed. So what we get here is the line where, okay, there's a read of size 4, it's in the file ob.c in line 5 and column 17. And the memory where we have this out-of-bounds read is part of the stack, that's part of the main function. So we have a very detailed error message here, which tells us pretty well what's happening here and gives very good guidance on how to fix this issue. This is a use after free bug. So no, this is not a use after free bug. Sorry, I blocked my slides. Can you read this? So, I mean, I hope most people probably already know what a use after free bug is, but we're allocating some memory, then we're accessing it, which is fine, and then we're freeing that memory, and then we're accessing it again. And these are like the bugs that happen all the time, especially in browsers and other complex applications. So I think most of the memory corruption vulnerabilities in browsers these days are used after free. And again, we compile it, and it prints 2 zeros. And then if we compile it with address sanitizer, then we get an error message again. And for the use after free, we get 3 important pieces of information. One is where it's been allocated, where it's been freed, and where it's used. So, yeah. So I've kind of made it my mission to test everything with Address Sanitizer, or at least all the software I use, and yeah, much more. Because I think really every project that's written with C code should test with Address Sanitizer. And I've seen so many pieces of software where I just had to run the executable and it would read some invalid memory. And really for core tools that are part of the Linux system. And what I then did was I thought, okay, can I build a whole Linux distribution where just everything is built with Address Sanitizer? I use Gentoo for this, but this is mainly because I'm familiar with Gentoo. So There's nothing Gentoo specific about it. Something similar could be done for other Linux distributions. It works. I can boot it. I can run it in a VM. I even have a VM with a server running on it. If you're interested and want to try to hack it, I could give you the IP. And just by doing this, like trying to create a system that has address sanitizer enabled, I found bugs in all kinds of packages, like from bash, core utils, mandb, which is the man page tool, Pigeon OTR, where it turned out that this bug was already reported half a year before, which is a bit bad for a security tool that like bugs keep lingering around in the bug tracker, and it was a use after free and maybe exploitable, so not good. Yeah, and all kinds of other stuff. So, and the next thing I'll try to do, so I can just via a script build all Gentoo packages with this and record the errors. I just have to get this into a somewhat usable format, and then I will publish that, and then via some crowd working process we could try to track down all these bugs. Yeah, and now I come to kind of the second topic of my talk, which is fuzzing. So on a very high level, you could say fuzzing is throw garbage at software. So what we're doing is actually just take a simple example. We have an image parser like libjpeg or libpng. And then we take some valid image, and then we just randomly add errors to it, which could be like some bit flips or just swapping some things around or just adding some characters, whatever. And then we test whether that crashes or not. And if we have a crash, it's very likely to be some kind of security vulnerability or memory corruption issue. Who of you has heard of the DARPA Cyber Grant Challenge? So a couple of you. So there were a couple of media reports, like here, watch AI hack into AI at DARPA Cyber Grant Challenge, or even Elon Musk says DARPA AI hacker challenge will lead to Skynet. So the general theme of these stories was, okay, there are some artificial intelligence computer bots that are in some shiny cases, like you can see on the lower left. And they are kind of fighting against each other and hacking each other and finding security vulnerabilities and patching them. So basically, all people that do IT security will soon be replaced by AI bots. So I will be replaced by an AI bot. And also, these computers will at some point create a Skynet and suppress humanity, and we will have a Matrix-like scenario. Okay, so I don't know how you feel. If I hear artificial intelligence these days, I get extremely skeptical. I believe a lot of things that are called AI are not really AI. And I wanted to learn a bit what's going on there. And especially if someone wants to replace me with an AI bot, I mean, I'm fine with that. Then, I don't know, maybe we can have some fancy utopian future where we don't have to work anymore. But I would like to know how that works. And I wanted to show a video, but we had some problem with the audio, and it's not that interesting. So what none of these media reports told was that all three winning teams of this competition were using American Fuzzy Lob, which is a fuzzing tool which I use all the time. So suddenly this was about something that I know quite well, because I don't know a whole lot about artificial intelligence, but I know a lot about fuzzing. And so basically what all of them did for the bug finding process, they used AFL with some additional customizations themselves. Yeah, I don't think that AFL will suppress humanity and build a Skynet, but it's pretty awesome. American Fuzzy Lob is the name of this rabbit breed here, but it's also the name of a tool. And to understand what it does, I have to go into historically how fuzzing was done. So the very simplest idea to do fuzzing is just to do random fuzzing. Like you add random errors to a file and see what happens. That's quite easy, but it's not very effective. So the more advanced, more complicated bugs you won't find with that. And then there's something which I call template-based fuzzing, which means you're trying to write a fuzzer specifically for some file format or some data structure. So you could do things like you have a JPEG and you add a -1 as the size and see if something bad happens with that, or you add the maximum size or a 0 for the size, which doesn't make sense, things like that. But this is a lot of work because you need to adapt your fuzzing for each file format you test. And therefore I say it doesn't really scale. If I want to test a lot of software with fuzzing, then this just doesn't work, at least if I'm doing it alone. And the kind of new idea that was popularized by AFL is coverage-based fuzzing. What's happening there is that the tool observes the code paths in the program that it's testing. And if it fuzzes something and it generates a new code path in the tool, then we'll say, okay, this is an interesting input, and it will save that input and use that input to further run the fuzzing process. American Fuzzy Lob made this idea popular. There were some earlier tools that tried similar things, but this is kind of the one where it got successful. And how you do this, so practically what you do is you compile your software with a specific compiler wrapper that adds this additional code to it so the fuzzer can see which code paths are triggered, and then you run the fuzzer itself. As earlier, I want to try to convince you that this is really easy. So you're compiling your program, you use configure, and then you use another compiler, so you pass a CC variable and a CXS variable, so the C and the C++ compiler. And it usually makes sense to use disable shared, because that means the application will not use separate libraries, but will compile all the libraries into the executable, and then you don't have to play around with LD preload and stuff, and it makes things easier. Then you put your sample input files into a directory, which I call usually in, but can be any name. And then you run the fuzzer with passing the in directory, some out directory, and then the path to whatever executable you're testing. And the add is then replaced with the input files from the fuzzer. And then you get something like this, which is a nice ASCII art screen. And there's a lot of information, and at least if you're starting, you can just ignore most of the information. The only really interesting things are in the upper right, which is the red number here is the number of crashes, and above is the number of paths. So the number of paths is interesting. If that stays at 1 or it grows very slowly, then usually something is wrong with your fuzzing process. Maybe the file is not really parsed. AFL found bugs in all kinds of important software projects like OpenSSL, OpenSSH, libjpeg, libpng, all the kind of stuff that you're using in your browser to parse web pages every day. GNU-PG, Bash, some of the stage fright vulnerabilities, they were big in the news last year. So I'm inclined to say there is basically no major piece of C code where AFL hasn't found any bugs. So it's extremely effective, and also shows us kind of how problematic the code base that we're building everything on is, because with such a relatively simple approach you can find that many bugs. So I talked earlier about address sanitizer, and now I talked about fuzzing, and the very obvious conclusion is to combine the two. Because if you use a fuzzer with a memory safety tool like address sanitizer, it will just find many more bugs. So that's what I usually do all the time when I'm fuzzing. I also enable address sanitizer. AFL has a function there that you just set an environment variable, AFL use ASIN, and you have to add this parameter mnon, which is the memory limit, because address sanitizer allocates a whole lot of virtual memory for its shadow memory. Now it's only virtual memory, so it doesn't really use it most of the time, but it's many terabytes. And so if you set a memory limit, it won't work. And the memory limit is there that not something cannot happen where like your application will use a lot of memory and everything crashes on your system. But in practice, this almost never happens. So I just disable the memory limit and everything's fine. Who remembers this? Yeah, I hope everyone. The Heartbleed bug was probably the most, bug with the most media reception. I wondered at some point, would it have been possible to find the Heartbleed bug with fuzzing techniques? And I thought it would be a cool thing if 1 year after Heartbleed I could say, hey, this is how you could find such bugs. So I tried that, and the challenge here is that it's a bug in the networking protocol, and AFL usually works on files, so you somehow need to translate that. And what I essentially did was I wrote a bit of OpenSSL code which did a handshake, but not really over network, but just by passing buffers back and forth. This does not always work. The OpenSSL API is very powerful and it has such features. In many other tools, this is not that easily possible because they don't have such an API. And then I added an option that you could just swap out a part of the handshake with something you passed on the command line. And so I could use a Wireshark dump or just write out part of the handshake and use that for my fuzzing. And after 6 hours, AFL was able to find Heartbleed. Then I published this, and a couple of days later I got an email from someone called Kostya Cerebrani, who is actually the guy who developed Address Sanitizer. And he was able to use a tool that I didn't know back then, which is called LibFuzzer, which found this bug in 5 minutes. So he basically replicated my experiment, but just with another fuzzing tool, and it was much faster. So what is LibFuzzer? LibFuzzer also uses coverage-based fuzzing. It's basically modeled after AFL. And also the two people developing LibFuzzer and AFL both work at Google, and I think they work in the same building, so they closely cooperate. And LibFuzzer is developed as part of LLVM and CLang. And the important difference between the two is that AFL fuzzes executables and LibFuzzer fuzzes functions. And that makes it just much faster because it's faster to call a function in C than to run an executable in Linux. But the downside of that is that it's more work because if you have a command line tool, you can just run this AFL command, and there you have to write at least a little bit of code for every time you want to fuzz something. And here's an example how this looks. So you basically, it's not a lot of code, but still you need to get this right, and there are some pitfalls in it. So this is fuzzing a function in OpenSSL, which is parsing some ASN1 data. ASN1 parsers are particularly prone for memory corruption vulnerabilities. So what it's doing here, it has a function that gets passed a buffer and a size. And then I'm passing this buffer and the size to this OpenSSL function. The important part is that I'm checking the return value, and if it has successfully parsed that, I'm freeing the structure that I just created. Because if I don't do this, then it will just grow to use more and more memory, and at some point it will crash because it's out of memory. So when you write this LibFuzzer code, you need to be careful to not have any memory leaks in the fuzzing code, because then it will at some point crash. Okay, and one thing which is maybe a bit of a more unusual use of a fuzzing tool. So the typical thing is that you're using fuzzing to find crashes, and which mostly means memory corruption vulnerabilities. And there's something which is called differential testing, where the idea is you have two functions that should do exactly the same thing. And then you compare the output. And if the output differs, something is wrong. And this doesn't work in a lot of situations because you need very clearly defined functions that cannot have any differences in any kind. But where it works very well is mathematics. So we all use cryptography, right? So, and it's kind of important, and cryptography is essentially applied mathematics. So we're doing calculations, which are often very simple things like multiplying things, exponentiation, and the question is here, is this mathematics correct? Is the software that we use for this producing correct results? And there was a bug in OpenSSL, was published early last year, where the squaring function of OpenSSL had a bug that on very rare inputs, and only 1 out of 2 to the power of 128 cases, it produced the wrong result. And to understand this, this is so rare that you will never hit this bug by chance. Like, you can do squaring until the end of your universe and you will not hit this bug by chance. But the surprising thing was that AFL was actually able to find this bug. This was first shown by Ralph Philipp Weinmann in a talk at Black Hat, which I recommend to watch. It was generally about big num vulnerabilities. It turns out that AFL is extremely good at finding big num vulnerabilities. So I tried this on a whole number of things. So always this strategy, I take an input, interpret it as a number or several numbers in some way, and then feed different implementations, like do a multiplication with OpenSSL and with libgcrypt and see if the result matches. So there was a bug in OpenSSL and the modular exponentiation, which is the RSA and Diffie-Hellman function, so it's kind of important. Unfortunately, nobody has really found out if this is exploitable or not, but yeah. Then in Nettle, which is the GNU TLS underlying library, there were several bugs in the elliptic curve multiplications. In NSS, there was also in the modular exponentiation and in the division. So this was the same bug because the modular exponentiation called the division function. In the poly 1305 authenticator in OpenSSL, this was fortunately found before it shipped in a release code. Recently I found a couple of issues in Matrix SSL, which is SSL library often used in embedded hardware. So this was a bit of a surprise that like you could use AFL to find bugs that are of a completely different kind than the bugs you usually find with it. One thing I end up having quite a bit of discussions about, which I find a bit annoying, is that most of the bugs I find with the fuzzer are out of bounds reads on the heap. And usually they are not very serious. They can be serious because Heartbleed was an out of bounds read on the heap. But very often it's reading some memory and it's not really doing anything with it. So it's unclear whether you call that a vulnerability. But there are some reasonable arguments to say why all of these instances should be called a vulnerability. Because essentially, if you're reading out of the bounds of a buffer, then the C standard says you cannot expect any deterministic behavior from your software. It can just do anything. So the compiler could optimize it in a way that whenever you read out of bounds of a heap, something very strange happens. I actually try to avoid these discussions when I can, because my opinion on that is I don't really care whether we call this a vulnerability or not. I think it's clear that these are bugs that should be fixed. So it's usually easier to just fix them than to debate whether it's a vulnerability. Then some more tools that I wanted to mention, at least quickly. So Address Sanitizer is kind of part of a suite of different sanitizer features that have all been developed by the same people. One other is Undefined Behavior Sanitizer, which finds also things where, similar to the out-of-bounds reads, where the C specification says you cannot do this, and whenever you do this, you cannot rely that your software does anything whatever you expect. The problem with this is that you will find a whole lot of bugs that are usually not very interesting. Most of them are invalid shift operations, actually. Then there's memory sanitizer, which finds uninitialized memory use. The problem with that is that it's a bit trickier to use because you not only need to compile your application with it, but also all dependencies. So if you want to compile something that uses a library, you need to make sure that the library is also compiled with a memory sanitizer. And if you're using C++ code, you even need to make sure that the part of the C library is compiled with memory sanitizer. And then there's thread sanitizer, which finds concurrency issues. I've never used that because these are usually not happening in the kind of software that I'm mostly testing. This is more interesting for larger projects, so this is Chrome has used this a lot. So this is an example for the kinds of bugs you can find with UBSAN. So what we're doing here first is we have a shift, and the shift is by the value j, and that's -1. And that's undefined. So C standard says you cannot do a shift by a negative value. And the other thing is an integer overflow. That's actually sometimes quite useful that it can detect integer overflows. And unlike the other sanitizer tools, undefined behavior sanitizer does not terminate the execution of your program. So you can find several bugs with it at once. So I have this code here as well. And I just add fsanitize undefined and also G. And you see we get output, shift exponent -1 is negative, signed integer overflow. So also very clear what's happening here. And here an example for memory sanitizers. So we have an array here, and we're setting one element to 1. And then we're trying to access the element based on the input variable argc, which is the number of parameters we passed on the command line, which includes the name of the executable. So if we execute this normally, nothing happens, because then argc will be 1, and it accesses the index 1, which we have set to a value. But if we set this, if we pass some parameter, we will see that we get an error here that use of uninitialized value. Again, we don't see a line number here. I don't know why. Below is the line number. Yeah. Okay, so that's memory sanitizer. There has been some effort to port these tools to the Linux kernel. So there's a kernel address sanitizer, kernel undefined behavior sanitizer, and so on. And these are just, you can enable, if you compile the kernel on your own with make menu config, then under the debugging features somewhere there's an option to just enable those. And there's also a tool called syscaller, which is trying to adapt this coverage-based fuzzing to the kernel and fuzz syscalls. And there have been a couple of other similar efforts. Like, for example, Oracle did some fuzzing on file systems. As far as I know, they have not published their code yet, which is a bit sad, but yeah. So, but this is like ongoing work that people are trying to adapt these ideas to the Linux kernel. Then what often comes up is network fuzzing, because these are usually the most interesting bugs. I mean, if you can kind of have a buffer overflow in your HTTP server or your TLS stack, that's an interesting thing to have, because then you can easily remotely exploit something. But it turns out that nobody has really found a very good solution for that, because it involves some complexities that you need to fiddle with timeouts, and how do you kind of get from a file to a network input. One approach is to have a library that you can preload, and that will basically intercept your network functions and simulate a network connection where it actually reads a file. One tool doing that is Preeny. And there's been a patch to AFL itself, which tries something similar, but it all turns out to be relatively fragile to use. And what usually works best is similar to what I have done with OpenSSL, that you have a wrapper that just you have a command line tool where you pass some input and it will be fed into a function. And this is also a recommendation. If people develop something like a web server, I would say this web server should ship a test tool which does parse HTTP header or something like that, because HTTP server needs to process HTTP requests. That's obvious. That's what it's doing. And this functionality should be available in a separate testing tool, separated from the whole code base, because that makes it much easier for other people to test this code with a fuzzing tool. Then one thing which is kind of ongoing research work, and where I'm not really sure what I think about it yet, is that people try to combine fuzzing with symbolic execution. So symbolic execution comes from the formal software analysis world, and the idea is essentially you're trying to find all the states that a program can get into by giving it an input. The problem with that is, as soon as you try to do this on real software, you will have so many states that it will just never finish. And the idea here is that if you use a fuzzer, and if this fuzzer is stuck and cannot get into certain parts of the code, that then you will try to use symbolic execution for it. So some people in the DARPA challenge have tried this. The problem with that is that they used an artificial operating system, which, and I'm not interested in an artificial operating system, I'm interested in real operating systems and real code. And I have not seen anything in that regard that I could use for normal software. And I must say I'm a bit skeptical about that. I feel that maybe it's easier to improve the fuzzing process itself. And I would like to see if there are bugs that you can find with this approach that you cannot find with normal fuzzing. So that would be interesting to analyze. Yeah, what's very important to mention is that all the tools I mentioned are free. So American Fuzzy Lob, LibFuzzer, Address Sanitizer, all of that, it's all free and open source software. So there's basically no reason not to use it. You can have it, you can modify it, play with it. It's yours. And this is something I want to mention, like, I mean, if you've been in a talk from Hannes, he's been saying since 10 years that we should just get rid of C and write code in safer languages. And like 10 years ago, I thought maybe he has a point, but it's never going to happen. And these days, I'm taking this much more seriously, because we have developments like Rust and the Servo engine, where Mozilla is trying to rebuild a browser in a safer programming language. And this seems to be really an idea that's catching on these days. And this makes me question, actually, if the things I'm doing are the right thing to do. Because most of the work I do is about the typical C kind of bugs. So we have buffers that are accessed outside of the boundaries. We have use after freeze. And there are ways in the programming language to avoid these kinds of bugs. So yeah, so maybe we should just rewrite everything in Rust. This is, I mean, people are joking about this, but I think this is a serious discussion we should have. What's the time?
We have around 15 minutes.
Okay, so I wanted to finish this with a small rant, which is anyone here from Red Hat? Okay, so couldn't make it. Yeah, so I decided to fuzz package managers, and the most important ones are obviously dpkg, which is used by Debian and Ubuntu and all the other derivatives from it, and the other one is RPM, which is used by Red Hat, SUSE, and yeah, some others as well. So for dpkg, I found 2 bugs. I think it were 2 stack overflows, and I reported them. And 8 days later, they published an update with fixes and a security advisory, both Debian and Ubuntu. I mean, that's pretty good, right? I mean, you cannot complain about this. It's pretty fast. It was a very smooth process. So yeah, that's good. Then I also fuzzed RPM. And I reported 3 bugs in the RPM parser. got as an answer, yeah, we just got 30 crashes in RPM. It will take some time till we can work on this. RPM. RPM is actually, originally it stood for Red Hat Package Manager, but today it stands for RPM Package Manager. And it has been declared an independent project in 2007 because it's not only used by Red Hat, it's also used by SUSE and some others. But actually the RPM website still belongs to Red Hat. But their security team told me that we don't own rpm.org domain, it's an upstream project, so there's not much we can do about it because I complained about their bug reporting process. So rpm.org is a track installation, and track has integrated bug tracker. So I thought, okay, I can report bugs in that bug tracker. And then I wanted to register an account, and I got a certificate error because the certificate didn't match the domain and was expired since 2012. And then I found even if I ignore the certificate warning, I could create an account. The CSS was broken, but I mean, didn't matter. But then I found out, okay, even then I couldn't create a bug because it says that I have to ask on the mailing list or in the IRC for permission to create a bug report. And that's kind of the point when you get really annoyed if you. And then I decided to report it to the Red Hat security team. RPM is developed on GitHub these days, but the webpage doesn't mention that. It's also interesting. If you actually want to know which is the latest release of it, you get a bit of confusing information. So the rpm.org webpage has a version 4.12.01. The GitHub repository says 4.12.0 is the latest version. Fedora is actually using 4.13.0, which is not really released anywhere, except there's a release candidate, but the Fedora package doesn't say it's a release candidate, it says a release, and even though, yeah, bit confusing. So the status right now, there's still a Stack Overflow that's unfixed in the latest Git code, and all the things I reported are unfixed. This must be 2013. Are unfixed because they haven't made a release for quite a long time. And there are more bugs, and as I had this discussion also in this case with people who said this is not really a serious issue because it checks the signature and it will never get to your bugs. I tried to fuzz the signature check itself, and I also found bugs. I'm not sure how serious they are, and I'm not really sure what to do about it right now because I'm wondering, maybe I should say I will only report this to you when you fix your development process. I don't know. Yeah. So, that was it. Thanks for listening. Please take away that you should test your software with Address Sanitizer and that you should fuzz your software. And if you have any questions, please ask them now. Yeah.
What do you do for software that reads random values? Can the American fuzzy lover can it also move random data from new random?
So what would be an I mean, you could probably just delete your urandom device and use that as an input. That would probably somehow work. I'm not sure. Do you have an example for an application, or? It seems an interesting idea to try to fuzz the output of a random number generator, because occasionally you have software that has different code paths depending on random numbers, like RSA encryptions, and there are tools to disable the random or make it deterministic, basically. It seems like an interesting idea to explore to like fuzz the random number input. Yeah. No, because it's an interesting. So the question was if I tried fuzzing Wi-Fi stacks. No, I haven't, but I think I remember that there were bugs found with AFL in WPA supplicant. But I'm not entirely sure how I would do that. I mean, it would probably take some work because you have this classic problem like how do you translate from your input to the networking function, and that's lower level networking, which may be even more complicated. But I've been wondering about Wi-Fi security quite a bit, and what I'd also be very interested is first the Wi-Fi stacks of firmware images, but I have no idea how to do that. Yeah, maybe with hardware, but
I guess, yeah, as a generalization of the Wi-Fi thing, have you done any fuzzing on kernel level things? Like you mentioned that in the tools.
I haven't really. I have once booted my system with Kernel address sanitizer, and it found a bunch of bugs in my graphics driver, but I haven't used any of the fuzzing tools because the impression was that this is kind of the more complicated stuff, and also it felt like quite a number of people are already doing this. So yeah.